In this video we'll be looking at vectors, and those of you that are taking physics, this will be a breeze for you and all of this will be very familiar. But for those that haven't had physics yet, then this could possibly be a new concept for you. And again, this is in our unit on solving right triangles, and vectors are an application where we can use right triangles. So quantities that have both a magnitude, which would be a size, and direction are known as vectors. Examples of vector quantities are forces, velocities, accelerations, and displacements. See those in physics often. Vectors are represented graphically with an arrow, a directed line segment, where the length of the arrow is proportional to the magnitude of the vector. Of course, the direction of the arrow represents the direction of the vectors. Okay, so for example, we could have a force. These are just examples of what a vector could look like. So if we have a horizontal here, and we have, for example, a 28-pound force like this, so the magnitude would be 28 pounds, and then from horizontal it's 31 degrees. So for example, this right here would be considered a vector, and that's 28 lbs, so 28 pounds, not 281 b's. Okay, so 28 lb. Velocity, so, and there's more than one way we can specify these, but if we have a north-south line and we're using our directional navigational, for example, could be heading back this way, and we would need to establish that angle there. We'll call it 203 degrees and 72 miles per hour. So our velocity is 72 miles per hour, and we have this angle here to describe its direction. So the magnitude is 72, the direction is 203 degrees from this vertical line. Displacement, so for example, we could have a north, south, east, west here. So north here, south here, west and east. And we could have a displacement like this, and we'll call that angle right there 60 degrees. And we're displacing this item 5 feet, for example. So our vector is this section right here. This is our vector. The magnitude is 5 feet, and the direction is described with this 60-degree angle off the north-south line. All right, let's look at the next section. Okay, let's read this section. Vectors can be resolved into two mutually perpendicular components, usually horizontal and vertical components. If our vector is a force represented by the symbol F, then the horizontal and vertical components are called F sub H and F sub V. So those are subscripts, so we say F sub H and F sub V. Or you could say F sub X and F sub Y for your horizontal, this one, and your vertical component, that one. All right, so example 4. The velocity of a bullet is 1,512 feet per second and inclines upward at 12 degrees. Resolve this velocity, call it V, into its horizontal and vertical components. So if we have our horizontal line here, like this, and our vector is up like this, and this would be our 1,512 feet per second. Velocity there, and then this would be our 12-degree angle. So this would be our velocity y, and this would be our velocity x. So velocity sub y, velocity sub x. So that's what they want. They want us to break it down into the horizontal component, this one, and the vertical component, this one. So our horizontal component, v sub x, we could say is equal to this. We can use this angle, and we have the hypotenuse. We want the adjacent, so we'll use cosine. So cosine of 12 degrees is equal to the adjacent side, v sub x, over the hypotenuse, 1512. So finally, v sub x is equal to 1512 times cosine of 12 degrees. We'll find that with the calculator in just a moment. And our vertical component, v sub y, then is going to be equal to the same thing, actually only we'll use sine. So sine of 12 degrees is equal to the opposite side, v sub y, over the hypotenuse, 1512. So our vertical component, v sub y, is equal to 1512 times sine of 12 degrees. And let's find those with our calculator here. So the vertical component, 15, 12, sine 12, and we get 314.36 for that one. So I'll write that here, equals 314.36. And then our horizontal component, 15, 12, cosine of 12 degrees is 1478. We'll round to 96, so 1478.96. So those are our two vertical and horizontal components of that vector, so feet per second for each of those. We want to keep the same units as our original vector had. All right, this next section here, addition of vectors. So we're combining multiple vectors. The sum of vectors is called the resultant. So when we put more than one vector together, we get a resultant vector. Vectors can be added by one of three methods: the parallelogram method, which we'll discuss here, and next head-to-tail method, and third component method. So let's start here with the parallelogram method. So they describe to us what to do. So I'll move the two vectors, keeping them parallel to their original directions, together tail to tail, and complete the parallelogram. The diagonal from the two joined tails to the opposite corner is the resultant, so the sum. So using the parallelogram method, graphically show the resultant R when adding vectors A and B. So if we take vector A here, it looks about like this, and we put vector B with it, the tail of vector B to the tail of vector A. So obviously, I think you understand, but this would be the tail of each vector, and these would be the heads. So the direction it's heading is the head of the vector, and the other end is the tail. So then we would make two parallels with that. So parallel to the vector A there would be like this. Parallel to vector B would be across here like this. So our resultant vector, use another color, would be from the tails of each to this corner of our parallelogram. So that would be our resultant vector there. So graphically, that's how it would look. All right, method 2 here, head to tail method, for adding any number of vectors. So we can have 3 or 4 or 5 or just 2, it doesn't matter. Move the vectors, keeping them parallel to their original directions so that they daisy chain together, so one right after the other, in a head to tail fashion. The resultant, the sum, is drawn from the tail of the first vector in the chain to the head of the last. So from the tail of the first to the head of the last. And it's not going to matter what order technically we put these in. The way we're going to do this one, we'll put A first. So we'll have vector A here, and then I'm going to use vector B here. So parallel to that would be about like this. That's vector B. And then C is coming back this way just a bit, like this. So that's vector C. So our resultant vector goes from the head of the first one, so A, from the tail of the first one, vector A, to the head of the last one. So that would be our resultant vector right there in red. Okay, third and final method, the component method. We break each vector, doesn't matter how many we have, into its two perpendicular components. So similar to that example 1 that we did earlier with the bullet example. Add all the horizontal components and call them the sum R sub H or R sub X, however you want to label it. And then add all the vertical components up and call the sum R sub V or R sub Y. So we're going to get a resultant horizontal component, this one, and a resultant vertical component there. Create the final resultant by adding these two vector components. All right, so let's use example 7 here to illustrate this. So using the component method, add vectors A, angle of elevation 40 degrees, and B, angle of depression 19 degrees. The magnitude of A is 107, and the magnitude of B is 51. Okay, so we'll start by finding the horizontal and vertical components of vector A. So they tell us that it has a magnitude of 107, so 107 here, and make a triangle out of it. So this would be our A sub Y, this is our A sub X, so our horizontal component here of that vector A, vertical component here. and it has an angle of elevation, so this angle right here would be 40 degrees. All right, so from there we can find each of those. So cosine of 40 degrees is equal to the adjacent side, a sub x, over the hypotenuse, 107. So our horizontal component of that vector is 107 cosine 40 degrees. And a sub y will be sine of 40 degrees is equal to the opposite side, a sub y, over the hypotenuse, 107. So our vertical component of that vector is equal to 107 sine 40. So let's pull our calculator up, find those. So 107 cosine 40 degrees gives me an a sub x value of 81.97. 81.97. They don't give me units on the magnitudes here, so we'll just leave it 81.97. And then I'm going to copy this down right here and change the cosine to sine, and that'll give us the vertical. So a sub y is equal to, use another color here, 68.78. Okay, so that's step one. Now we need to find vector b, so I'm going to get us some more space here. All right, so we've got vector b here. We'll make a triangle out of it. So it has an angle of depression of 19 degrees, so this angle in the top left corner of that triangle is 19 degrees. So our horizontal is b sub x, our vertical is b sub y, and the magnitude of b is 51. So the hypotenuse now of our right triangle here, and we need a right angle there too, is 51, and then whatever the units are here. So that means b sub x is going to be equal to cosine 19 is equal to b sub x over 51. So finally, b sub x is going to be 51 cosine 19, cosine of 19 degrees. And I think you are probably seeing a pattern here. That means our vertical component, b sub y, is going to be equal to sine of 19 degrees is equal to b sub y over 51, because from the 19-degree angle, the opposite side is b sub y. So finally, b sub y is 51 sine 19. So we'll minimize that, put these in our calculator. So 51 cosine 19 is our horizontal component. So we'll use another color here. So b sub x then is equal to 48.22. b sub y is same thing, only sine. So 51 sine of 19 degrees. And that gives us 16.6. And it's important to know we've got our b sub x and b sub y here. If you notice in our drawing here, our b sub y, the vertical, it's going down, so we need to make this negative. So now that we have all of our components, get our, for our vector A here, our horizontal component is 81.97, and our vertical component was 68.78. That was from this up here. Now we can combine them. So our resultant horizontal vector would be the 48.22 plus 81.97. Those are both positive. Our resultant y will take the 68.78 and subtract the 16.6 from it. So those values become 1.97, 130.19 for the horizontal resultant component, and then 68.78 minus 16.6 gives us resultant vertical component of 52.18. So now we can draw a triangle from that. So we'll have our resultant horizontal component labeled 130.19. Our resultant vertical, it is upward, 52.18, like this. It is upward because it's positive. Had it been negative, we would draw it down here like this. And then resultant, the actual resultant vector r would be there. We can use Pythagorean theorem here to find the magnitude of that vector. So r is equal to the square root of 130.19 squared plus 52.18 squared, just using Pythagorean theorem. So let's type that in the calculator. 130.19 squared plus 52.18 squared. And we're square rooting that quantity, and we get 140.26. So our resultant magnitude is 140.26. And then we need direction, so we need this angle theta here. There's more than one way we can do it. I'll use tan inverse to find it. Remember, when we find angle measures, we use the inverse, tan inverse, cosine inverse, sine inverse. So tan inverse of opposite from our angle theta is 52.18. And adjacent from our angle theta here, this would be the adjacent side, 130.19. Got to be in degree mode. We are. So tan inverse 52.18 divided by 130.19. And we'll get our angle theta and we'll be done. And that is 21.84 degrees. So 21.84 degrees. So we have a direction of our resultant, 21.84 degrees, and we have a magnitude of our resultant, 140.26, and we are done with this problem and done with this video.